Hey everyone, so we're going to continue our discussion about energy, and we're going to go into a slight deep dive in the other types of energy, the main ones being potential and kinetic. For the most part, the only thing you really need to know about for this video at least is just the equation. We're going to do a few practice questions for each one, not actually probably one for each one, because the equations themselves are pretty basic and it's just a plug and chug. What ends up being more important is how we end up applying these equations later on, and that's going to be in a future video. So we're going to start with potential energy, probably one of the most common ones. As I mentioned before, the idea about potential energy is that it's stored energy, it's energy that this object has or the system has that can be converted into kinetic energy. It just hasn't yet. Now, the one that we're going to be focusing on right now is the potential energy that's caused by gravitational forces. So the gravitational potential energy, which is represented as U sub G. I mentioned before that there is another common type that we're going to talk about, spring potential, but we haven't talked anything about springs. That's actually going to be the third part of this entire unit. We'll talk about the spring potential energy. And again, it just ends up being another thing to add in. But for now, I just want to focus on as few types of energies at first until you get a little bit more comfortable. And then I'll add in that last type of potential energy. But the main gist of this is the potential energy stored in the system caused by the gravitational force acting on it. That gravitational force constantly trying to pull the object down to a lower height. So this is caused anytime an object is raised to some height within a gravitational field. I forgot to actually add in that qualifier, mostly because of the fact that there's almost always a gravitational field, so that wasn't really necessary. But anytime an object is raised to some height, there is gravitational potential energy. So the greater the height, the greater the gravitational potential the object has. So here's a question: is what is the height of this block? Well, this is just kind of a thought process, but it depends on the scenario. So if we had a block that is 1 meter above the table and the table is 1.5 meters up, it depends on how you want to define height. Are we defining it to the table? Are we defining it to the floor? If there is a pit, do I do it to the bottom of the pit? It depends on the scenario. Usually, what I recommend is unless they specifically say what that height is supposed to represent, I usually go by that the height is whatever the lowest point that the object is going to reach. In this scenario, when you release this block, it is going to hit the table first and foremost, and then it's going to stop its motion there. So it's more useful to talk about height as if it's only going to the table and that everything else below it is just not there. Because again, it's not worthwhile. If the if this object was going to hit this and then go to the floor, then I might consider the floor to be the bottom. But again, it's whatever floats your boat. You can choose whatever it is as long as you are consistent throughout the entire problem. And that's actually the key thing, is that you have to be consistent. If you say this ground is going to be 0 just because that makes life easier for you, then you have to make sure that you realize that this point still has potential energy. Uh, so because of the fact that we're talking about height and it's based off of where we're measuring the height from. Again, in the previous case, it depends on whether we're considering the height to the table, to the floor, to the bottom of the pit. Um, what we talk about instead is not just gravitational potential energy in a constant sense, but in the sense of the change in the gravitational potential energy that the object has. Going back here, when we compare this point to this point, we're saying that this point has a specific amount of potential energy greater than this point. So if we say that this has a gravitational potential of 50 joules, what we're really saying is that this point, this object at this point, has 50 joules more potential than this point down here. That's really what we talk about when we say gravitational potential energy, because we're usually almost always exclusively talking about change in gravitational potential energy. Now, one question I could also ask is, besides height, what other things could affect the gravitational potential energy, and what you think that the equation might end up being? The equation ends up being this: delta UG equals mg delta y. So the change in gravitational potential energy is going to be based off of the mass acting on the object, the gravitational acceleration that the object is experiencing, and the change in height. Oftentimes, though, you're probably going to see me be a little bit on the lazier side and drop the deltas. It honestly doesn't matter in this case. I guess it's probably better form to keep the deltas in there, but you know, again, what you could, if you want, you could replace the y, the delta y, with just h. That's also a slightly simplified form. One interesting thing, though, is that this is actually coming from the equation for work. I mentioned before that work can be specified depending on the specific force. It turns out that the work being done by gravity is the gravitational force. If we look back to the equation for work, work equals force times displacement. For an object that is lifted at some height and will, fall straight down, the work or the force is the force of gravity, which is Fg equals mg, and we're going to times that by the displacement or the height that the object is, delta y. So this equation really is just a reworked version of the work equation. Now, one thing that I need to clarify, it seems very stupid, but it's actually extremely important for this unit, is that objects cannot have potential energy, only systems can. I sort of talked a little bit about the concept of objects and systems. This ends up becoming a much bigger part in the energy unit. The idea being that sometimes what you might see is they might talk about the uh, a mass, and they might ask about some type of energies that the mass has, or they might call it the mass dash Earth system. The idea is that if you just ask what is the potential energy of a pencil, that is technically not an appropriate question because the pencil itself cannot have any type of energy because the in order to have the gravitational potential energy, you need the force of gravity. You need that gravitational acceleration, that gravitational field trying to pull the object down. So the only system that can have energy is a mass Earth system. A lot of times, what you'll end up doing is you'll look at what the system is, and each term is going to tell you what type of energy it has. Uh, I'll talk about that in a lot more detail when we get to the conservation of energy part. So we'll do a practice question. So pause video, work self, and we'll go over a second. All right. So here you can actually see an example of what I was referring to. They're looking what is the gravitational potential energy of the woman Earth system. So here we are actually clarifying that yes, we could have potential energy. It is important to note that some questions are a little bit more simplistic, and you may see the Earth part being dropped out because it's almost always there. But just be aware of that because there are some questions, and I will show them where that will be kind of the trick involved. And here they want us to, they actually specify where we're taking the gravitational potential energy from. We're doing it relative to the ground. So we're just going to use the equation, mgh. Again, you can see that I'm dropping the deltas because, like I said, it's pretty much always there. It's assumed to always be there. 60 times 10 times 40, and we get 24,000 joules. All right. Now, there is another form of this potential energy equation. Again, if we actually go back to what I said before about how the potential energy is just a reworked version of the work equation, where the work is the force of gravity. Well, there's two equations for force of gravity. There's the simplistic form when we're on Earth, where we say Fg equals mg, but there's also the big G equation. Fg equals g m1 m2 over r squared. So this equation will end up being used very similar to that one when we start talking about massive objects. If we want to know the potential energy between planets and moons and stars. Uh, and the nice thing about this is that it looks very similar to the big G equation, where it's g m1 m2 over r instead of r squared. One thing to note is that there is a negative symbol in here. Now you might be wondering why is that? Uh, this kind of goes with the way that this equation's worked. If we look back to the equation for ug equals mg delta y, if you look at that equation, as the height increases, the gravitational potential also increases. So as delta y increases, ug increases. Easy enough. The problem is, if we look at this equation, g m1 m2 over r, if I do that same idea and I increase r, I increase the distance I am away from the planet, the g m1 m2 over r goes down. this delta, because the r is in the denominator, as r goes up, the whole term goes to a smaller value. Well, that ends up being a conflict with what we had in the previous equation. So how do we fix it? We make this negative so that even though the number is getting smaller, it's getting smaller in the negative direction, meaning that it's actually getting closer to zero and increasing to zero. It's a little bit weird. It kind of throws things for a loop. Just be aware that it is in there. This equation you don't have to memorize. It is on the reference table. The negative is on it in the reference table. It's just, like I said, kind of like a weird thing. The good thing is that you're barely going to be using this equation. This is kind of a one and done. You use it and then that's it. There's really nothing crazy being done with this. Um, Now, one other thing that you might notice is you might notice that the delta was dropped. This delta is not being, I didn't drop it because I'm being lazy. It's actually because of the fact that we are doing a delta, but the other change is being set equal to zero when the object is infinitely far away. So when it's infinitely far away, the potential is zero. So we can actually just get rid of the delta again. We don't have to, specify that. All right. So let's just do a quick practice with it. So pause the video, work itself, and we'll go over in a second. All right, so these are the constants on the reagent's reference table. So we just take the numbers, plug it in, and we get our answer. Again, nothing crazy, and that's it. And we have to make sure we keep that negative in there. All right, and this is going to be the last energy that we talk about, kinetic energy. We talked about that kinetic energy is the energy that an object moves. Well, what other factors could affect kinetic energy? If we consider the case of a ball being rolled on the floor, and we think about what else could we change about that in order to make it hurt more, um, and you should come up with the idea that speed is a factor, but also mass is a factor. So the equation ends up being k equals 1/2 mv squared. So this is the equation for kinetic energy. Um, this actually can also be derived using the equation for work, where we assume that the object starts at rest. Um, and then the other thing that I need to mention is objects and systems can both have kinetic energy. So if we go back to that previous scenario where I had woman dash earth system, the woman qualifier, the mass, that means that I'm allowed kinetic energy, and then the earth qualifier means that I'm allowed potential energy. So woman dash earth system means that that system is allowed both kinetic and potential energy. If I just said the woman, she's only allowed kinetic energy. Again, you'll see a few examples of when that is important to keep in mind. All right. So here's a practice question. Pause the video, work self, and we'll go over in a second. All right. So again, the equation is pretty much a straight shot. We have our equation, we plug our numbers in, and we get an answer. Easy peasy, lemon squeezy. And that's pretty much it for the other major types of energies. You might be wondering why I didn't do anything with heat. That's because that doesn't have its own specific equation. That's usually found through the concept of the energy being lost, or it's being found using the work equation where the force is being the force of friction. So I'm not doing anything with heat right now. We'll see it in a later problem. But if you have any other questions, feel free to let me know. Otherwise, good luck and have a great day.